Sometimes a machinist can look at a metal part and swear it is perfectly round. Then the part goes into service. It spins at speed. The oil film thins to almost nothing. The load hammers the metal thousands of times a minute, and suddenly the eye is no longer good enough. Tiny errors turn into disasters. Not round enough, and the bearing runs hot. Not concentric enough, and the shaft starts to vibrate. Then one day the whole production line begins to scream like a horse. That is the end of it. The line shuts down. Maintenance takes over. Production stops. American machine tool history is full of famous giants, massive lathes, heavy milling machines, boring mills, planers, transfer lines. But there was another class of technology that drew far less attention. These were not the machines that carved a new shape out of raw stock. They came afterward. They took a part that was merely close and pushed it to the state modern industry actually needed. Rounder, smoother, more concentric, more repeatable, and almost impossibly exact. That was the world of precision grinding. And in 1909, in a small town in Vermont, William LeRoy Bryant founded a company to turn that simple idea into an industry. How do you grind parts held in chucks, internal bores, inside and outside diameters, bearing races, and circular surfaces until the remaining error almost disappears from human perception? In this video, we are tracing the story of the Vermont grinding machine that chased perfect roundness all the way down to the micron. If you enjoy stories about the companies, people, and decisions that shape the industrial world, subscribe to the Gear Archive and follow along. First, we need to answer a basic question. Why did roundness become such a bottleneck in manufacturing? Most machinery depends on flatness. Flat surfaces are the foundation of machines, but roundness is what allows machines to rotate. When a shaft spins inside a bearing, its geometry cannot be merely approximate. When a ball bearing race carries dozens of hardened steel balls around a track, that surface cannot wander and ripple at will. When pistons, bushings, gears, spindles, housings, and engine parts work continuously, geometric error becomes heat, vibration, noise, and wear. And in mass production, the problem becomes much worse. A skilled machinist can rescue one part. The automobile industry does not need one part. It needs thousands, then millions, all effectively the same. Aviation does not need one engine that runs well in a test room. It needs many engines that can survive vibration, temperature, load, and flight time. By the early 20th century, American industry was entering the age of high-speed production. Automobiles were beginning to move from luxury goods into mass manufacture. Aviation was leaving the experimental stage. Machine tools were getting faster, steel was improving, grinding wheels were improving. But the faster industry moved, the clearer one fact became: cutting metal was not enough. A lathe could turn stock into a near cylinder. A drill and a boring tool could make a hole. A mill could generate surfaces and slots. But after those operations were finished, many parts still had to be ground. Grinding did not merely brighten a surface. It corrected the small remaining errors. It improved roundness. It stabilized size. It created surfaces that oil films, bearings, and high-speed motion could live with. The bottleneck was that the parts needing grinding were not always easy to hold. A long shaft could run between centers, but a short part, a ring, a bushing, a compact housing, or a turned semi-finished component often had to be held in a chuck. And once a chuck enters the problem, the challenge is no longer just rotating the work. The challenge is holding it truly on center, bringing the wheel exactly where it belongs, controlling the size, and repeating the process fast enough for production. That is why machinists became so familiar with a phrase like chucking grinder. It referred to a whole class of grinding machines built for parts held in chucks, usually as second operation work after turning or rough machining. This was exactly the kind of work the automotive industry, the bearing trade, precision equipment makers, and the defense sector increasingly needed. So the early 20th century demanded a new generation of grinders, faster, more accurate, more automatic, and better suited to quantity production. Bryant arrived at exactly the right time. William LeRoy Bryant, usually called Roy Bryant, was no amateur. He came out of one of the most remarkable machine tool environments in America, Springfield, Vermont. The town had no obvious advantage like Pittsburgh with steel, Detroit with automobiles, or the coastal cities of New England with ports. What it had was something even more important, an unusually dense concentration of inventive masters. Springfield sat in what became known as Vermont's Precision Valley. Jones Lamson Machine Tool Company had moved there from Windsor in 1888 under the leadership of James Hartness. Hartness was an inventor and executive, later the governor of Vermont, and most importantly for this story, a mentor to a generation of machine tool builders. Under Hartness, Jones Lamson was not just a factory. It became an unofficial school for mechanical engineers. Edwin Fellows left that world to found the Fellows Gear Shaper Company in 1896. Fred P. Lovejoy founded Lovejoy Tool Company. William L. Bryant founded the Bryant Chucking Grinder Company. Together, these firms turned Springfield into a machine tool center far more influential than the town's size would ever suggest. Bryant joined Jones Lamson in 1897. By 1899, he was head of the drafting department. By 1905, he had become chief engineer. In a machine tool company, the draftsman and designer must understand cutting forces, bearings, castings, tolerances, drives, cutting tools, and the operator at the machine. A bad drawing does not merely make an ugly machine. It makes a machine that cannot be built, aligned, or trusted to hold tolerance. While working with Jones Lamson chucking lathes, Bryant saw a problem that had not been properly solved. After turning, many parts still needed grinding in a second operation. If that grinding was done slowly, the line choked. If it was done inaccurately, the value of precision turning was lost. Out of that problem, Bryant developed a multi-spindle grinding machine for second operation work. James Hartness encouraged him to strike out on his own. Hartness also helped provide the initial financing and became the first president of the Bryant Chucking Grinder Company. Roy Bryant later assumed leadership himself. In 1909, the Bryant Chucking Grinder Company was established in Springfield, Vermont. A year later, in 1910, the company built a plant of roughly 20,000 square feet directly across from Jones Lamson. That same year, Bryant shipped 9 machines to Ford and Cadillac, aiming straight at the most important industrial market in America, Detroit. It was a shrewd move. To understand Bryant, it helps to understand the difference between shaping and finishing. A lathe creates form. It spins the work and uses a cutting tool to bring the metal near its intended diameter. A lathe can be extremely accurate, but the tool still leaves tool marks, cutting forces, slight distortion, and small geometric errors. For some parts, that may be enough. For simple shafts or lightly loaded components, near enough can be good enough, but for bearing races, bores, bushings, thrust faces, engine parts, and precision mechanisms, near enough is not enough. A grinding wheel does not cut like a single-point lathe tool. It is made of countless abrasive grains, each removing a tiny amount of material. The result is that grinding can control size and surface in ways rougher cutting processes struggle to match. But grinding also generates heat. It demands rigidity. It demands a good spindle. It demands a method of holding the work without distorting it, and in mass production, it also demands speed. Bryant's chucking grinders attacked that problem from the production side. The part was clamped in a chuck or fixture and rotated. The wheel approached the surface to be finished. Depending on the configuration, the machine could handle outside diameters, inside diameters, or related surfaces. With multi-spindle design, multiple tasks could be performed in parallel or in a more tightly organized sequence. That transformed grinding from a slow, isolated operation into a production step with rhythm. And the critical point was not merely absolute accuracy, it was repeatable accuracy. A machine that can produce one good part does not change an industry. A machine has to produce the first good part, the second good part, the 100th, and the 1000th. A factory manager does not only ask whether a machine can grind, he asks whether it can hold size through an entire shift, whether it is easy to set, whether the output remains consistent. Bryant built its reputation by answering those questions well. In the 1930s, as the Great Depression forced many machine tool builders out of business, Bryant used the slower market to improve its designs. Manual machines were developed toward semi-automatic operation. Hydraulic drives replaced some pneumatic systems. Automatic sizing options appeared. Motorized spindles were introduced rather than relying entirely on gear or belt transmission. These sound like technical refinements, but their meaning was practical. Semi-automatic meant the operator did not have to execute every motion by hand. Hydraulics meant smoother and stronger motion. Automatic sizing meant the machine could move closer to knowing for itself when the part had reached size. Self-powered spindles meant greater control with fewer layers of mechanical transmission. All of it pushed Bryant in the same direction, precision grinding at production speed. That was why the company steadily expanded into automotive work, aviation, bearing manufacture, and precision equipment. Each industry had its own demands, but all of them needed the same things: round parts, accurate bores, fine surfaces, and repeatability. When Bryant shipped 9 machines to Ford and Cadillac in 1910, it was still only beginning to step out from the shadow of Jones and Lamson. But those orders showed that the automobile industry had already recognized the value of precision grinding. Ford and Cadillac did not buy machine tools for curiosity's sake. They bought them because automobile production required thousands of rotating and sliding parts: engines, transmissions, shafts, bearings, bushings, drive assemblies, and accessory mechanisms all depended on small geometry. A car might be sold on styling and power, but its reliability lived inside the parts the buyer never saw. Then came the First World War. By 1917, the Bryant plant had doubled in size and was running 3 shifts a day. The company leased additional space from Jones and Lamson to help produce artillery shells. Wartime demand also pushed Bryant to develop 2 new machine models for the aircraft industry. One of the most significant milestones came through the Ford Aircraft Division. During the First World War, Ford's aviation operation used 102 Bryant machines in the manufacture of Liberty engines. That was no trivial detail. The Liberty engine was one of America's major wartime efforts to standardize and rapidly produce aircraft engines. And if an aircraft engine requires large numbers of precision parts, then grinders like Bryant sit directly inside that capability. Bryant's reputation for precision grew from there. According to historical material later cited by Vermont Machine Tool, from the First World War through the interwar years and into the Second World War, much of the grinding work done on aircraft engines was performed on Bryant machines. After aviation, Bryant moved deeply into the bearing industry. That made perfect sense. Bearings are one of the harshest tests of circular geometry. The inner ring, the outer ring, the raceway, the faces, the finish, and the concentricity all affect friction, temperature, noise, and life. A good bearing is not merely good steel. It is good steel machined to the correct geometry. As automobiles, industrial machinery, aircraft, and military equipment demanded more bearings, precision grinding became part of the industrial foundation. Roy Bryant remained president and general manager until his death in 1931. He was succeeded as president by E.J. Fulham, then treasurer of the Fellows Company. That detail also reveals how tightly Springfield's industrial network was woven together. Jones and Lamson, Fellows, Bryant and Lovejoy were not just geographically close. They shared people, capital, technical knowledge, engineering culture, and a common vision of precision manufacturing. During the Great Depression, many machine tool firms were crushed as factories across America stopped buying new equipment. Bryant survived because its product occupied the part of production where customers still needed precision and productivity. Exports also helped some American builders endure. In the 1920s and 1930s, the Soviet Union became a major customer for various American industrial firms, including Ford and some machine tool manufacturers. But Bryant did not simply wait for the market to recover. It used the hard years to improve the machines. That mattered when the world moved toward another war. Before the Second World War, Bryant was already an important name. The war pushed everything to another scale. In 1938, Bryant's sales tripled. In 1940, the United States Army Ordnance Department asked the company to expand its plant to roughly 127,000 square feet. By 1942, the workforce had grown to around 1,350 people, including about 200 women. Those numbers tell us something important. They tell us that grinding had ceased to be a secondary concern. In industrial war, precision grinding was a strategic capability. If engine parts, bearings, control mechanisms, aircraft components, and complex assemblies could not be ground accurately, weapons production slowed. An airplane does not merely need aluminum and horsepower. It needs thousands of rotating surfaces, bores, and round parts that function correctly under load. Demand became so high that, like many wartime manufacturers, Bryant saw its products built under license by other concerns. During the war, Bryant also manufactured certain radar units for Raytheon and General Electric. That points to another side of American machine tool companies. They did not merely build machines for others. When war demanded it, they could become manufacturers of precision equipment in their own right, a company fluent in spindles, grinding wheels, bearings, chucks, and tolerances already possessed much of the technical foundation needed to produce far more complex devices under government direction. The war also left a larger lesson. Industrial power does not reside in a single invention. It resides in a network. Bryant needed steel, bearings, grinding wheels, motors, assemblers, engineers, inspectors, suppliers, military customers, and neighboring companies. Springfield, Vermont became one node in that larger system. During the Second World War, Springfield's importance was so great that the U.S. government reportedly ranked Springfield, together with the nearby Cone Automatic Machine Company in Windsor, as the seventh most important bombing target in the event of an attack on American industrial capacity. That sounds strange for a small Vermont town. But once you understand machine tools as the machines that make other machines, it becomes logical. Destroy the machine tool base, and you cripple the ability to replace, repair, and expand production. In 1946, Joseph B. Johnson, a longtime Bryant employee who would later become governor of Vermont, became vice president and general manager. The company entered the post-war era with a strong reputation, export markets, and deep experience in aviation, bearings, and defense work. But the post-war machine tool world was not going to stand still. After the war, Bryant remained a strong company, but the structure of the industry was changing. The Korean War drove demand upward again. In the mid-1950s, Bryant's expertise in precision spindles opened a path into a new field, drum memory for computers. At first glance, that sounds unrelated. Technically, it made perfect sense. Drum memory required precise rotating assemblies, fine surfaces, and highly refined mechanical manufacture. A company skilled in grinding and spindle design was well positioned to enter that kind of work. In 1958, Excello Corporation of Detroit acquired Bryant. After the sale, Bryant's computer product activity grew rapidly and was eventually moved to Walled Lake, Michigan, where it was folded into another Excello division. This was a familiar turning point in American machine tool history. An independent company became a division inside a larger corporation. That could bring capital, broader markets, and a larger network, but it could also strip away some local identity and autonomy. Bryant did not disappear overnight, but from this point onward, its story was no longer only the story of Roy Bryant and Springfield. During the Cold War, precision grinding also became a geopolitical issue. In the early 1960s, the U.S. Department of Commerce blocked Bryant from carrying out a major order for the Soviet Union. The reason was straightforward. Precision grinding machines were not only civilian tools, they could improve military capability. A machine able to grind small parts to high precision could serve the production of bearings, gyros, guidance mechanisms, engines, and systems no strategic rival was supposed to possess at the highest level. In 1972, Bryant acquired the line of precision external centerless grinders from the Van Norman Machine Tool Company. Around the same period, Soviet contracts continued to generate controversy. One proposed sale of 45 precision grinding machines to the Soviet Union drew criticism because it might help improve intercontinental ballistic missile accuracy and multiple warhead capability. This was the darker side of precision machine tools. The machine itself has no political beliefs. It simply holds tolerance. But tolerance is power. The same ability to grind accurately can produce bearings for trucks, shafts for industrial machinery, or components for weapons systems. Governments in the 20th century understood that very well. Bryant also entered the era of numerical control. In 1980, Bryant introduced the Lectroline LL3 and demonstrated it at the International Manufacturing Technology Show. According to Bryant's own historical record, the LL3 was described as the world's first numerically controlled multi-surface grinding machine. The LL1, LL2, and LL4 followed, extending the range from very small internal diameters to very large outside diameters. It should have been the beginning of a brilliant new chapter. But new technology does not always save an old corporate structure. In 1986, XLO and its subsidiaries, including Bryant, were acquired by Textron. In 1988, Textron sold Bryant to the Goldman Group, a financial investment organization. Historical accounts of Bryant suggest that the new owners had limited experience in the machine tool business, and the result was a difficult period for the company, its customers, and its suppliers. In February 2002, Bryant Grinder shut down abruptly. Many believed the Bryant name might never return. It was a familiar moment in American industrial history. A company that had survived wars, the Depression, the rise of automobiles, aviation, and numerical control nearly died in peacetime because of ownership structure, management, and a shifting industrial economy. But the Bryant story did not end in 2002. In July of that year, Vermont Machine Tool purchased Bryant Grinder and continued operating it in the CNC grinding market. That preserved the most important part of the legacy: the technology, the service knowledge, the spare parts, the technical memory, and customer trust. In 2015, Fives acquired Bryant's technology, intellectual property, and service operations. The Bryant line was then developed within the Fives Landis system in Hagerstown, Maryland. It was an ending that was both sad and realistic. Bryant was no longer the independent Springfield company of Roy Bryant's day, but its name, engineering, and applications continued inside a global machine tool group. So after all the rise and all the collapse, what exactly was left behind? First, Bryant solved the right problem. Roundness does not happen by itself. It has to be designed, fixtured, ground, measured, corrected, and repeated. Every silent bearing ring inside an industrial machine depends on a chain of technologies behind it. Every automobile line, aircraft plant, and defense facility depends on that chain. Solve the right problem, and you can create an entire industry around it. Second, Bryant demonstrates the power of the industrial cluster. Springfield, Vermont did not become Precision Valley because of one company alone. It became that because of an ecosystem. James Hartness at Jones Lamson, Edwin Fellows with gear shaping, Roy Bryant with chucking grinders, Lovejoy with tooling, and the draftsmen, assemblers, inspectors, salesmen, and managers who sustained a culture of precision. When one skilled man left to found his own company, the ecosystem did not lose capability. It multiplied it. Third, Bryant is a reminder that machine tools are strategic power. In peacetime, Bryant grinders made automotive parts, bearing races, and industrial components. In war, they entered aircraft engines, defense production, radar, and supply chains the government considered vital. During the Cold War, they became sensitive exports because geometric accuracy could become military strength. A grinding machine does not need a flag to have geopolitical value. It only needs to make tolerances others still cannot. And finally, Bryant teaches the fragility of industrial legacy. A company can live for nearly a century, possess superb products, strategic customers, rare technical knowledge, and a respected name, and still be threatened by conglomerate ownership, financial management, changing markets, and the weakening of its domestic industrial base. Bryant did not become vulnerable because roundness stopped mattering. Roundness still matters. Bryant became vulnerable because the company behind that capability had to survive in an economic world changing faster than its old structure could bear. But like so many American machine tool names, the iron and the ideas outlived the sign on the building. An old Bryant machine can still stand in a shop today, paint worn thin, hand wheels polished by decades of use, spindles still turning, grinding wheels still singing that familiar note when it touches steel. A modern engineer can look at a CNC grinding machine from fives and still trace a line running backward through Lectraline LL3, Ford, Cadillac, Springfield, James Hartness, and Roy Bryant. That is Bryant's real legacy. And in an industrial world built on rotating motion, it remains a small but indispensable part of manufacturing power. If you enjoyed this video, like, subscribe to the Gear Archive, and leave a comment with your thoughts. Thanks for watching, and I'll see you in the next one.